Hi, my dear students. Today we will learn about electrostatic boundary conditions. Here, in previous classes we learned about different properties of electric field. Okay, then we see that mainly there are three fundamental parameters in electrostatics. They are charge density, potential, and electric field. Okay. Now we want to check what happens to electric field when it moves from one medium to another. Okay. Then first of all, for this analysis, that means the behavior of the electric field in a boundary. Okay. Boundary means when it travels from one medium to another, what happens to it at boundary. Okay. That is what we want to learn now. So first of all, we consider a thin sheet of charge distribution. Okay, so for that, consider a surface of charge density sigma. Okay, charge density sigma. Electric field travels from one side of the surface to the other. This is a boundary. Okay, this surface is a boundary. Surface acts as a boundary. Okay. So I think I can draw here the figure. For example, consider a surface like this. Okay. This surface has surface charge density sigma. Okay. This one has surface charge density sigma. And the light travels from this side to this side. Okay. This is the surface. Now, we already learned about the properties of electric field using two equations. Okay? Using the divergence of electric field and the curl of electric field. Okay? That means we already learned about del dot E equal to rho by epsilon 0. Okay, this is Gauss law, or you can write this as the form of an integral equation, surface integral, closed surface integral, E dot dA. E represent the electric field, rho represent the charge density. Okay, E dot dA equal to Q enclosed by epsilon 0. Okay, this is one of the equation. Equation 1. Similarly, electric field is characterized by the second equation. Also, together these two, this is called curl del cross E equal to 0. Okay, or closed line integral E dot dl equal to 0. Okay. Using these two equations, we can uniquely describe our vector field here, the electric field. Okay, in the Helmholtz theorem from the first chapter itself, we learned that if you know the divergence and the curl of a vector field, you can uniquely describe the field. Okay, similarly, here we write the two equations, the divergence of electric field and the curl of electric field. Okay, using these two equations, we can find out what happens to electric field when it crosses a surface with surface charge density sigma. Okay. And so, for doing this, first we want to check this Gauss law. Okay. First part is Gauss law. Then we can check the curl. Okay. First Gauss law. For this, we assume a Gaussian pillbox here, like this. A Gaussian pillbox. Okay, this Gaussian pillbox have thickness epsilon here, like this. Epsilon is very small. This pillbox is such that its upper surface lies just above the surface and its lower surface lies just below the surface. Okay, this is the pillbox, and this epsilon is very small because this is a boundary, a thin surface. Okay, so this is a boundary, that means its thickness is nearly 0. Epsilon tends to 0. This is the pillbox, and this pillbox has area A. We assume that the pillbox has area A, upper surface area A. Okay, now for doing this part, we know that here the component of electric field parallel to this aerial vector contributes. Okay, component of electric field parallel to this aerial vector contributes. So for this closed surface, you can see that here the upper surface has aerial vector like this. Okay, so we can assume here the electric field by taking its two components such that the component of electric field perpendicular to this boundary. Okay, for example, I can show here, this is the upper component of electric field. It is called E perpendicular above. Okay, and here this is E perpendicular below the surface. Okay, this electric field is called E perpendicular just because this is the component of electric field perpendicular to this boundary. Okay, similarly there is the component of electric field parallel to this boundary. Okay, so first of all we treat this case. Okay, so here, for in this case, the surface integral of E dot dA, we can check this Q enclosed by epsilon 0. For this Gaussian pillbox, okay, for this Gaussian pillbox, this surface integral of E dot dA equal to Q enclosed by epsilon 0. Q enclosed by epsilon 0 means Q enclosed by this pillbox. Actually, the surface charge density is sigma. So, the Q enclosed by this pillbox is sigma A. Okay. Q enclosed by this pillbox is sigma A. Sigma is the surface charge density of this surface and E is the area of this pillbox. So, you get here sigma A by epsilon 0. Okay. Sigma A by epsilon 0. Now, we want to find out this closed surface integral E dot dA. For this part, here, for this upper surface of this pillbox, the aerial vector points along this. Okay, that means this aerial vector is parallel to this perpendicular component of electric field. Okay, aerial vector is parallel to this perpendicular component of electric field. So, you can write here, this is equal to E perpendicular above into A. Now what happens? Similarly, there is a lower surface also. But for lower surface, this aerial vector is pointing downward. Okay? Aerial vector is pointing downward. But this electric field vector is pointing upward. So there is a minus sign here. Okay? Minus E perpendicular below A. Okay. Now what happens? Now there are 4 other sides. How is these 4 sides? These 4 sides are with this thickness epsilon, right? One of this thickness is epsilon. So if you want to find out this, for each surface there is an aerial vector and you have to take the component of electric field along this aerial vector. Okay? Component of electric field along this aerial vector, then only you get the corresponding components here. But for in this boundary, for this surface, since the surface is itself is very small, very thin surface, thin boundary, we can treat this epsilon tends to 0. That means this aerial components, area itself goes to 0. Okay. So for all other components, this area goes to 0. I can write here. That means this plus. Okay. I think I can erase this part and write. Okay. So here. This surface integral of E dot dA equal to E perpendicular above A minus E perpendicular below A. Okay. Then we have to add all other 4 components. Okay, all other 4 components means aerial, this area, and the component of electric field along this direction. And similarly for this all other sides. Okay, but we assume a thin surface. Okay, a very thin surface. So we can assume this area itself goes to 0. Only these terms contribute. Okay. I can write here all other terms, all other surface area tends to 0. Okay, that means epsilon tends to 0. So all other 4 surfaces, their area tends to 0. So there is no need of taking the component. Okay, otherwise you have to take the component of electric field along this aerial direction. Okay, but now we assume this epsilon is very small. So you can assume this area tends to 0 and so this contribute only this much. Now you can compare this with our this equation sigma A by epsilon 0. So I can write here E perpendicular above minus E perpendicular below. Okay. Into A equal to sigma A by epsilon 0. Okay. Sigma A by epsilon 0. Cancelling this A, you get here E perpendicular above E perpendicular below equals sigma by epsilon 0. Okay, sigma by epsilon 0. Now, this is all about our Gauss law. The Gauss law itself gives us this condition for the perpendicular component of electric field. Okay, only the perpendicular component of electric field survive in this case of Gauss law. Okay, now we want to consider the second equation, the curl. Okay, del cross E. This is one of our result. Okay, now we can check the second equation, del cross E. Okay, the second condition, del cross E. Del cross E equal to 0, which implies closed surface integral E dot dl equal to 0. Okay, this is the condition. Okay, for that again we assume the same surface here. Okay, same surface. And now this time we know that we have to apply this closed loop, curl law. Okay, so for that I take a closed loop like this. This loop is crossing this surface. Okay, because this upper surface is above this surface and this is the lower surface like this. Okay, this is epsilon. Okay, now we apply this closed integral E dot dl along this part. From this diagram itself you can see that now we want to take the component of electric field along this line. Okay, that means along the surface. That means tangential component of electric field. Since this tangential component is parallel to this surface, I write here, okay, I write here E parallel, okay, E parallel. Here E parallel above, for this line E parallel above. Let this loop has length L, okay, length L, and this side has length epsilon. This epsilon is very small because we already discussed that this surface is a thin surface. Okay, so epsilon is very small value and this E parallel above L. Okay, E parallel above L. Now in this side, this dl is opposite to the direction of parallel component. So here again a minus sign. E parallel below L. Okay, what about these components? As we already discussed, this epsilon is very small. And if you take the component of electric field along this direction of epsilon, this term goes to 0. Okay, so this equal to 0 because epsilon tends to 0. Okay, here this epsilon represents this length of this loop. Okay, so now what happens? This means E parallel above equals E parallel below. Okay, E parallel above equals E parallel below. Okay. E parallel above equals E parallel below. Okay, so using the two laws of electric field, that means the divergence and curl, we can deduce the boundary conditions for electric field. Is it clear? Okay, so I think I can write now these laws together. Okay, now for boundary condition I write just BC. BC for electrostatics. Okay, electrostatics. What are the BC? They are E perpendicular above minus E perpendicular below equal to sigma by epsilon 0. Okay, similarly E parallel above equals E parallel below. Okay, so you can join these two equations together and write this, because you know that this is for perpendicular component, this is for parallel component. So jointly we can write this equation as electric field above minus electric field below equals sigma by epsilon 0 n cap. Okay, this n cap represents the direction of normal vector. Okay, n cap. So for the first case, this case E perpendicular is parallel to this component, so you get this equation, and E parallel is perpendicular to this one, and so this goes to 0. You have E parallel above minus E parallel below equal to 0, because sigma by epsilon 0 is along the normal direction. Okay, these are the electrostatic boundary conditions for electric field. Okay, so here what is our conclusion? Conclusion is that the normal component of electric field, the normal component of electric field is discontinuous. Okay, is discontinuous at the boundary with surface charge density sigma. Okay, with surface charge density sigma. If this surface charge density at the boundary is 0, okay, if the surface charge density at the boundary is 0, then the electric field is continuous. Remember that thing also. Okay, so if this sigma is 0, in that case both components are continuous. Okay, hope that you get the point, because here in this session we find out the electrostatic boundary conditions for electric field. Okay, so already we learned that we can uniquely define an electric field using its divergence and curl. Okay, so the divergence is called Gauss law, which is written as del dot E equal to rho by epsilon 0, or in integral form, closed surface integral E dot dA equal to Q enclosed by epsilon 0. Similarly, its curl is defined as del cross E equal to 0, or closed line integral E dot dl equal to 0. Okay. Now, using these two, we have to find out the characteristics of our electric field. Okay. So for that we assume a thin boundary because we want to find out what happens to electric field when it crosses a boundary. Okay. So we assume a thin boundary of thickness epsilon. Okay. Very thin boundary. And we assume a very thin boundary and use a pillbox whose thickness is epsilon. Okay. Pillbox with a thickness epsilon. And using this pillbox, we apply Gauss law and found that the perpendicular component of electric field is discontinuous if there is a surface charge density sigma. And in the case of the curl del cross E, we find out that the parallel component of electric field, okay, the parallel component of electric field is continuous always. Okay, so finally we conclude that if the boundary has no surface charge density, then the electric field is completely continuous. That means there is no discontinuity. Discontinuity happens only if the boundary has surface charge density sigma. And you can combine these two conditions together like this. This is called electrostatic boundary conditions. Okay. Electrostatic boundary conditions. This epsilon 0 is dielectric permittivity. We already learned it. And this sigma is called surface charge density. Here we use epsilon to represent the thickness of the pillbox. Okay. We can check what happens to the potential at the boundary. Okay. Potential. Okay, so potential above minus potential below is equal to minus integral A to B E dot dn. Okay, that means if the surface is like this here, there is a surface like this. Okay, we already discussed the surface, and we take this line like this, crossing the surface. This is A and this is B. Okay, this is the surface, and then minus integral A to B E dot dl gives us V above minus V below. Okay. Now, we know that this thickness of this surface, this boundary is negligibly small, and so its length tends to 0, and so this is equal to 0. Okay, this is equal to 0 because the thickness is very small. Okay, the thickness of the surface is nearly 0. Okay, nearly 0. Okay, nearly 0. Very small. Okay, so this term equal to 0. That means potential above equal to potential below. That means electric potential is always continuous. Okay? Electric potential is always continuous across a boundary. But electric field is discontinuous. Normal component of electric field is discontinuous across a surface with surface charge density sigma. But here the potential is continuous always. If there is a surface charge or not, that is not a problem for potential. It's always continuous. Okay. But you know that this electric field equal to minus grade V. We already proved it. For electrostatics, E equal to negative gradient of potential. Okay. So this holds for electric field again. Okay. That means gradient V above. Okay. If you take gradient of this, gradient above minus gradient below, V below, is equal to minus sigma by epsilon 0 n cap. Okay, because this gradient of potential holds the discontinuity just like this electric field, because you know that electric field is given by negative gradient of this potential. So gradient of potential is discontinuous like this. Okay, now you can write this equation in another way, just like dou V by dou N, component of grade V along the direction of n cap, that is dou V by dou N. Okay, dou V n by dou N above, dou V above dou N minus dou V below dou N equal to minus sigma by epsilon 0. Okay. Now, where dou V by dou N equal to gradient V dot n cap. Component of gradient V along the direction of n cap. Okay. So, this is all about the potential. Now, we can wind up the session. The boundary conditions for electrostatics. Here we see that the electric field is discontinuous if there is a surface charge density. The normal component of electric field is discontinuous and the tangential component is continuous. Okay, but as far as the potential is concerned, it is always continuous. But its gradient, negative gradient of potential is called electric field. Okay, so the negative gradient of potential is discontinuous if there is a surface charge density. Okay, so learn well. Thank you.